Right here, we've got the notes for section 4.7. This is using the normal to approximate a binomial. So here's our requirements. Sample size n from a population, so you know the probability of success, p, conducting n independent trials, and then n times p and n times q both have to be more than 5. So remember, q is the probability of failure. So if you're doing a normal distribution, the average value is found by multiplying the number of trials by the probability of success. Standard deviation is found by taking the square root of the number of trials times probability of failure. Now, the problem here is that lots of things we talk about are not necessarily continuous measurements. Like you can't have 4.5 coin flips. You can have 4 or 5. So that's what this continuity correction deals with. So it says when using a normal approximation, adjust a discrete whole number x by using a continuity correction so that x is represented between x minus 1.5 or x minus 0.5 to x plus 0.5. So if I'm looking for exactly 15, I'd go between 14.5 and 15.5 because those would round essentially to 15. Okay, so example 1, in 431 NFL football games that went to overtime, the teams that won the coin toss went on to win 235 of those games. If the coin toss method is fair, we expect the teams winning the coin toss will win about 50% of the games, so we'd expect 215.5 wins in 431 overtime games. Assuming there's a 0.5 probability of winning the game after winning the coin toss, or assuming that the coin toss is fair, find the probability of getting 235 winning games among the 431 teams that won the coin toss. That is, given this, find at least 235 wins. So I need to find my parameters first. So mu is equal to n times p. So 431 times 0.5. So 431 times 0.5. So that's my 215.5, which they actually gave me in the problem. And then the standard deviation is the square root of n times p, which is probability of winning the game. And also q is the same number because these two have to add up to 1. So 431 times 0.5 times 0.5, and then I take the square root, and I get 10 point, what do we want to call this? 38, we'll say. Okay, so now I need to calculate my z-score. So I'm looking for at least 235 wins. So that means I need more than 235. So I'm actually going to round this down. So it's going to be 234.5 because that's the smallest number that'll still round up to 235. Minus what the average should be divided by the standard deviation. And all this goes to my calculator, 234.5 minus 215.5 divided by 10.38. And I get a z-score of 1.83. Now remember, z-scores always give me probabilities of less than 234.5. So when I look this up, that's a positive z-score, so I need the positive side of my table. 1.83, so 1.8, 0, 1, 2, 3, so 0.9664. So 0.9664. So the likelihood of winning fewer than 235 games is that. So the likelihood of winning more than, which is what the question is actually asking, is 1 minus this, which is 0.0336, I believe. That's what the number that I need is. So if the coin toss is fair, and we found out that we won 235 games out of the 431 that won the coin toss, this is the likelihood that that would actually happen with a fair coin toss. So since this probability, or with the coin toss method being fair, sorry, it's not the coin toss itself that's fair, but if winning the coin toss only gets you a 50% chance of victory, meaning that the other team has an equal chance of winning, so the coin toss is unimportant, this is the likelihood of getting those 235 wins. Since this probability is so low, our assumption is wrong. The coin toss is not a fair method of running the overtime because this probability is so low. It's very unlikely that assuming the coin toss is a fair method, we would get 235 wins. Okay, so this brings us to continuity correction. So this is kind of what we talked about before. So it gives us kind of a breakdown. So if your statement says at least X, you find the area to the right of your value minus a half. More than to the right of your value plus a half, because you can't include your value. at most to the left. So these two, we'd have to do our 1 minus step. The one I did on the previous example, just find the area to the right, you have to do 1 minus because our tables are set up to the left. For these two, for the at most or fewer than, you can just read the value straight off the table. These are left of, which is our table set up to do. Exactly x, you actually find two z-scores, find the probabilities, and then to get between, you take the difference in those values. So, which is what this is going to talk about. So using the same information from example 1, find the probability of exactly 235 wins. That is given blah, 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 find exactly 235. So we're doing the exactly here. So the average was 215.5. Our standard deviation was 10.38. I'm just copying these numbers down from the previous problem. So I need to find two z-scores. One when I do minus the 0.5, so that'd be 234.5 minus 215.5 over 10.38. So value I'm looking for minus the average divided by the standard deviation. And the other one is the plus 0.5, so 235.5 minus 215.5 over 10.38. So the one on the left, I think that's the one we just did, but I'll work it out again. So 234.5 minus 215.5 divided by 10.38. So this is a z-score of 1.83. Over here, 235.5 minus 215.5 divided by 10.38 is a z-score of 1.93. So now we need to convert these into probabilities. So the probability here, 1.83, that's the one that we just did. That was 0.9664. And I do need to look up 1.93 though in my table. So positive side of the table again, 1.90123, so 9732. So 0.9732. So the likelihood of winning exactly 235 is the difference between these two numbers. So 0.9732 minus 0.9664. So that's a very small number, 0.0068 is your likelihood of winning exactly 235 games with that coin toss. So it's pretty unlikely that you'll win exactly 235 games, which makes sense. That's one outcome out of the 431, so the individual probability is most likely pretty small. Okay, that brings us to the end of the section and of the unit.